Hi, I am Sanjay Patel. In this lecture, we are going to understand how to transform a triple integral into spherical coordinate system. I will be taking two problems to understand this process. So, in this direction, let us solve some two interesting examples. The first one, find the value of the triple integral over the volume V of 1 upon x square plus y square plus z square raised to 3 by 2 dx dy dz, where capital V is the volume lying between the two spheres x square plus y square plus z square is equal to a square, and x square plus y square plus z square is equal to b square, where a is less than or equal to b. By changing it into spherical coordinate system, Okay, so you want to find the value of this triple integral where the volume is the region between the two spheres x square plus y square plus z square is equal to a square. That is a sphere with center 0, 0, 0 and the radius a. So let us solve this. First of all, we'll try to draw the figure, and remember that the radius of the two spheres are a and b respectively, and the center is same, so they are concentric spheres. So first of all, I will just keep the figure which I have already prepared. So this is my let us write this way. Okay. Fine. So this is the situation. The sphere with a small radius, that is the yellow sphere, I will take as its equation as x square plus y square plus z square is equal to a square. So let me write this way. This is the sphere whose equation is x square plus y square plus z square is equal to a square. And the sphere with the larger radius, that is b, is x square plus y square plus z square is equal to b square. Okay. So our region of integration is the volume between these two spheres. So this is our region of integration. Okay. Okay, let me. Okay. Now this thing, this radius, small radius, is a, and this radius is b. Okay. Now we transform this integral into spherical coordinate system. Transforming the given integral, the given triple integral into spherical coordinates, by taking, the relation between the Cartesian and spherical as x is equal to r sine theta cos phi, y is equal to r sine theta sin phi, and z is equal to r cos theta. Okay, and what is r, theta and phi here? They are the spherical coordinates of any point. Suppose if I take any point in this region, so any point somewhere here in the space, say P, whose coordinates are r, theta and phi, then what is the meaning of r, theta, phi? We join this P and the origin with a straight line. Okay, so this is your r, and if we draw perpendicular from point P onto the xy plane, okay, and suppose this M is the foot of the perpendicular, then we join the origin and this foot of the perpendicular. Okay, change this color. No. Okay, so we get this thing. Oops. So in this case, this angle made by the line segment OP with the z-axis, this angle is theta. This angle made by the line segment OM with the x-axis is phi. Okay, and our region of integration is the volume between the two spheres. So this phi changes from say this point, and it goes on and takes the full round, and you will get phi from 0 to the full circular rotation, and you will get phi varies from 0 to 2 pi in this region. So it is clear that in this case phi is from 0 to 2 pi, and since theta is the angle between this OP and z-axis, that point P can be anywhere. It can be here also, or it can be here also. So according to the position of point P, the theta will change from say if it is here, it is 0, because angle between OP and z-axis will be 0 if the point is here. If the point is here, then angle between the line segment OP and z-axis, positive z-axis, will be pi. So just note that here in our case, okay, in this case, we have 0 less than or equal to phi less than or equal to 2 pi, and theta is lying between 0 and pi. Okay, 0 and pi. So That is one thing. And also from these equations, what we can conclude is x square plus y square plus z square is equal to r square, which is also known to us. Okay. And further, just recall that when you transform Cartesian variables x, y, z in R3 into spherical coordinate system, then we have dx, dy, and dz. This differential is replaced by r square into sine theta into dr, d theta, and d phi. Okay, so therefore the given integral, that is the integral of the function 1 upon x square plus y square plus z square raised to 3 by 2 dx, dy, dz over the volume V, we can express as, let us see how does all this changes. First of all, let me write the triple integral over the new volume, that is V dash, in the spherical system, and this x, y, z are replaced by these relations. So we'll get x square plus y square plus z square is equal to r square, that raised to 3 by 2. dx, dy, dz is replaced by r square into sine theta into dr, d theta, and d phi. So now we want to determine the limits of r, theta, and phi in this given region of integration. See, what is r? R is the length of this line segment. In this volume, that r changes from this inner sphere to the outer sphere. So r changes from this sphere to this sphere. What is the equation of this sphere in terms of spherical coordinates? This is given by r square is equal to b square, or you can say r is equal to plus or minus b, or simply let us write r is equal to p. And this is same way, we have r is equal to plus or minus a. So in this first quadrant, or you can say equation of this, in the first quadrant, octant is r is equal to a to r is equal to b. So equation of this is r is equal to a, and equation of this outer sphere is r is equal to b. What I am concentrating is only on the first octant, means where x, y, z are all positive. So this triple integral I can write as 8 times, because I want to take only the positive octant where x, y, z all are positive. So I will get 1 upon say r cube, means 1 upon r into sine theta dr, d theta, d phi. Okay, that required integral is equal to 8 times the value of the integral in the first octant. In this region, in the first octant, which is something like this, I can explain this way. So this is our sphere, something like this, and there is another sphere. Okay, and that r changes from this to inner sphere to outer sphere. So I can write down this limits of integration for r, theta, and phi in this manner. The r varies from a to b. Okay, then that theta varies from 0 to pi, as we have seen, and this for the third integral, phi varies from 0 to this theta varies from, which is the angle here, so theta varies from 0 to pi by 2 only. So I can add 0 to pi by 2, and phi varies from again 0 to pi by 2 in this first octant. 0 to pi by 2. Phi is the angle between this line segment and the x-axis, which is here. Let me show you in this figure again. We are taking only the first octant, so only this part. So phi varies from, say, this 0 to pi by 2, and theta also in the first octant varies from 0 to pi by 2. So what we can write here is phi varies from 0 to pi by 2, then that is 1 upon r sine theta dr, d theta and d phi. And note that all the limits of integration are constants, and these functions, each of this term does not contain the other variable. So I can rewrite this as 8 into r is equal to a to b 1 upon r dr into theta is equal to 0 to pi by 2 sine theta d theta into phi is equal to 0 to pi by 2 again into d phi, that is integration of 1. So it is a very simple problem. So 8 into integral of r is log of mod r, and r is equal to a to b into integral of sine theta is minus cos theta, and it is from 0 to pi by 2 into integral of 1 is phi, because variable is phi now, and phi is equal to 0 to pi by 2. So just simplifying this, what we are going to get is 8 into log of mod b minus log of a into minus cos pi by 2 minus minus plus cos 0, okay, into pi by 2 minus 0 for the third integral. So it is 8 times log mod b upon a into cos 0 is 1 plus 0, and this is pi by 2, so into pi by 2. So the final answer is 4 times pi into log of mod of b upon a. Okay, so this way you can find the value of this triple integral. Okay, let us take another example. The second example I want to take here is this. Find the value of the triple integral over the volume V 1 upon say square root of 1 minus x square minus y square minus z square into dx dy dz, where capital V is the volume of the sphere, x square plus y square plus z square is equal to 1, lying in the positive octant, positive, or you can say first octant. Okay. So first of all, I will try to draw the figure for this. So let me draw the figure. So the region of integration is the volume enclosed by the sphere in the first octant or the positive octant. Let me keep that figure which I already prepared. Okay. Let's keep it over here. Now in this you can see our region of integration is only this much, lying in the first octant. So I can consider this way. This is positive, say x-axis, positive y-axis and z-axis. So here also we'll change this into spherical coordinate system. Here given here is having center 0 and radius, center origin and radius is 1. Okay, fine. So we transform this transforming the given integral into spherical coordinate system by taking again the same thing, x equal to r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r into cos theta. Just remember that in our region of integration, that is in the first octant, that is only in this portion, that theta, if you take any point on the sphere and draw a perpendicular, then and if you join these two, this is your r, and if you draw a perpendicular here and then join this foot of the perpendicular, then this angle is phi and this angle is theta. In the first quadrant, theta varies from, you can see, 0 to pi by 2, and the angle phi also varies from 0 to pi by 2 in the first octant only. Okay, this phi varies from this point to this point, means from x-axis to this y-axis in the first quadrant, and here theta varies from, say, from this z-axis to the xy plane, so it varies from 0 to pi by 2 again, while r varies from this 0 to the sphere. So this point is on the sphere, where the equation of this surface is actually in the spherical system is r is equal to 1. This is same as r is equal to 1, because in the spherical coordinate system we know x square plus y square plus z square is equal to r square. So I can say that the given integral, which is triple integral over the volume V of what was that? It was 1 upon square root of 1 upon square root of 1 minus x square minus y square minus z square dx dy dz. This is equal to triple integral over a new volume in the spherical coordinate system of 1 upon square root of 1 minus r square, because these three equations gives you x square plus y square plus z square is equal to r square. So I can replace this by r square, and this differential dx into dy into dz is replaced by r square into sine theta, as you know, that is r square into sine theta, that is the Jacobian value, into dr, d theta and d phi. Okay, so like this. Now, as we have discussed, I can write down the limits of integration for this new triple integral. Say r varies from 0 to 1, that is from the origin to the sphere, and theta, as we have discussed, varies from 0 to pi by 2, and phi also varies from 0 to pi by 2. 1 upon square root of 1 minus r square sine theta dr, d theta and d phi. Okay, so just let us understand again. Here r varies from this point to this point on the sphere. So r varies from 0 to, say, this sphere which is r equal to 1. Theta varies from 0 to pi by 2, and phi also varies from 0 to pi by 2. Okay, so here in this case 0 less than or equal to theta less than or equal to pi by 2 in the first quadrant, and phi is also between 0 to pi by 2, while r changes from 0 to r is equal to 1 from this figure. So I can now find the value of this integral by writing this triple integral as the product of three integrals, single integrals, because all the variables are not, all the functions are independent of the other variables, and limits of integrations is also constant. So I can rewrite it like this: dr into integral theta equal to 0 to pi by 2 sine theta d theta into phi equal to 0 to pi by 2, and there is no term like phi, so I can write 1 d phi. It's a matter of computing these three integrals, which is very simple. To find the value of this integral, let me add and subtract 1 here, and let us see what happens. So what I want to do here is, this is equal to r is equal to 0 to 1, say 1 minus r square, and say what should I do, 1 minus r square minus 1. What I want is this term, so minus 1, okay, like this. But this minus sign is not there, so first I'm writing minus sign here. Or let me explain a different way. What I want to do here is, first I multiply this by minus 1, so I will write minus r square upon square root of 1 minus r square. Okay, then add and subtract 1, so 1 and minus 1. Okay, so I can write like this into, this is very simple, integral of sine theta is minus cos theta, and limits are 0 to pi by 2, and integral of 1 is phi, and limits are 0 to pi by 2. Okay, so this gives us the value of this integral cos theta, that is cos pi by 2 is 0 and cos 0 is 1, and we'll get 1 only, and this I can write as minus integral r is equal to 0 to 1, say 1 minus r square upon square root of 1 minus r square minus 1 upon square root of 1 minus r square dr into 1 into pi by 2. The value of this integral is 1, and value of this integral is pi by 2. So finally what I will get here is minus pi by 2 into integral r equal to 0 to 1. This we can write as square root of 1 minus r square dr, and minus integral r is equal to 0 to 1 upon square root of 1 minus r square dr. Okay, so now it is a simple problem to find the value of this integral. Okay, we know the value of there is a standard formula for this, for integrating square root of 1 minus r square, and also for the other part. Or can we do something else? No, 1 minus r square. So I can take r is equal to, say, sine theta here, right? To integrate this, so 1 minus sine theta, sine square theta is cos theta, so that is fine. And we can integrate this very easily. Let me call this as result number 1, and I will now calculate both the integrals separately in order to avoid the confusion. So first, this is simple, r equal to 0 to 1 upon square root of 1 minus r square dr, that is sine inverse r is equal to 0 to 1. So value of this is sine inverse 1 minus sine inverse 0. So it is pi by 2 minus 0, which is equal to pi by 2. So this is one thing. And for this integral, okay, I will take, for integral r is equal to 0 to 1 square root of 1 minus r square dr. We can use a formula, or let us use some substitution. I can take, say, r is equal to sine t, some new substitution. So dr is equal to cos t dt. Okay, so this I can write as integral 1 minus sine square t is cos square t, and the square root is there, so it is cos t, and dr is cos t into dt. Dr is again cos t into dt, right? Okay, and when r is equal to 0, sin t equal to 0. So let me write here, r is equal to 0 implies t is equal to 0, and when r is equal to 1, we have t is equal to pi by 2. So t is equal to 0 to pi by 2. So this is cos square t. So integral 0 to pi by 2 cos square t dt, and we can use the reduction formula. So it is n minus 1 upon n, okay, into, since it is even, into pi by 2. So that is 1 by 2 into pi by 2, means it is pi by 4. So this is my second result. Putting these two values of a and b in this result number 1, what we'll get is the required integral. Therefore, the integral, I will not write it again, this is equal to minus pi by 2 and this minus this. Okay, so minus pi by 2 is there, into the first integral is this first integral is this b, this is b and this is a. This value is minus, or rather plus pi by 4, and minus the value of this integral, that is pi by 2 from result A, we will get pi by 2. So it is minus pi by 2 into minus pi by 4. So it is nothing but pi square by 8. Okay. So this is the final answer. This way you can find the value of triple integral by transforming the given Cartesian variables into spherical coordinate system, so that the problem becomes very easy. Okay, so this way you can take some other problems for practice and understand this concept in more detail, how to determine the limits of integration. So thank you and goodbye.